Okay, that'd be happy to chat. Sean, are you gonna present both of these? I mean, the three, and then there's something I have to admit for sharing. I just gave up on it and used my watch. So. You get the three, and then there's a button to push. And Kristen, that's put the time in. You are not. Yes, which doesn't bring it up. Then you've got to play, I think, after you get. Oh, there you go. You're good. Okay, you've got it all figured out. This Kevin. We need this guy right here. And I'm gonna duck out. Oh, no.
There's many more things to do with it.
Oh, that's the way it goes. That's
I've almost mastered the avocado.
I mean, we could just catch Lester.
I'm having to use the WebEx because I can't see the screen under it.
They haven't been showing it on me.
It's because it's not working.
Oh.
We are the first meeting that they've had.
It's an hour. It's an invited. It's according to schedule. Oh, we get all the answers.
I don't know, look at somebody.
Sure.
We're just finished.
That wasn't me.
I'm sure that's this time.
It's okay. Because I never hear anything. I don't know what. I don't seem to hang out.
Okay. George, let's let her rip, man. It's already ready? Yes.
Okay, so time to come to order. So three of the 5 talks in this session are people who know me, and they're all remote. So there has to be some message in that. We're going to start with Luca Casagrande, and he and I have carried on intermittent correspondence on calibration for 15 years, but we've never met each other. Pardon?
Break is on.
How do I mute the whole planet?
Don't want to mute. I think it's Kathy.
Well, let's.
Yeah. Keep going, George.
Yeah, just let her
keep
rip.
going.
I think we want to bring Luca on and start.
So he's recorded, and Kevin in the control room has paused. So as soon as
Go.
you wave to him, he'll start.
Start.
So everybody knows that we're the test pilots for the new.
So it's supposedly there's a record up top?
Yeah.
So we're going to test everything.
We have to be happy so
I think he's coming down. Today is 23rd. I'm just thinking of it is that right?
This is all I have. I don't think it's being heard. I didn't realize this was a recorded talk. I'm sorry, guys. Jesus.
Carlos, we could jump ahead if we need to. Come back.
There's no audio coming in.
Sean is certainly here.
It's supposed to be local, but
This goes on.
it would be good to stay as close to the time as we can. Luke is calling from Australia.
Yeah, no.
Whatever time you said, I think it's like 4:30 in the
Yeah.
morning. I've just been offline all day.
All right, I have that. Okay. Let me check something.
It's good, good. But not the audio, so it's.
He's working now, he's working on
Yeah. No, but it's good.
it. Since they're not here, wait for him, he's gonna go do something. Stand by, continue standing by. I'm thinking of filling.
It's Maria for a new band.
Little soft shit.
Response.
She said she would. Fair enough.
Pick her again. So she has the absent-minded professor thing part right now. The absent-minded professor who just lets go.
And it's never.
He's working on it. And have answers for you. This work here.
So do we know?
What that means. It's like,
Advice to me, try.
it's that way. What's the other way?
That's the next slide.
Why is it not labeled?
Something else we should.
Don't publish.
Something else.
We can play this and we can just try guessing the words of it.
You're not gonna do now.
Reminds me of your class when it was like full of them missing.
Oh, yeah.
Which one is it of these three?
That's okay.
I like.
I was there, like this is.
What happened to my chill pill?
Person could have given us.
Where's my chill pill?
I have your name on my email already.
Yeah, we probably talked to them. So, short, get back here on time. As you have to do. Trust you.
I think, I thought that the other gentlemen. I'm pretty sure I don't have to. And I thought
overlap.
they were acting up people. And now I think it's,
What happens?
Turns out that it's hard.
No, I'm very excited. Oh, you did the sacrificial lamb thing?
So let's bring up Carlos's talk. He gives grace.
And, it's like, oh, can you see the asteroid? All right. Tracy,
It's up to you, sir.
Nice.
Okay, well, due to technical difficulties.
Rotation of the Earth. And so if you.
Okay.
Past San Juan, actually, when we do the surveys, we use the microphone.
Hey, can you hear me well? Yes. Perfect. So, thank you very much to the organizer for giving me this opportunity to present you some of the techniques that we are using for the calibration of multi-filter surveys. And we're interested in that because in my institution, we run an observatory that is designed to make large area, that in this context means thousands of square degrees, multi-filter, that means dozens of passbands surveys. The Observatorio Astrofísico de Javalambre, the OIG, is located in Spain. You can see the arrow. The image shows the light pollution in continental Europe, and we are basically in a dark spot. So this is one of the most underpopulated regions in Europe. We have no light pollution. Also, we have high mountains with very competitive scene. So 15 years ago, we started the construction of a dedicated observatory. We have 2 telescopes with 2 panoramic cameras dedicated to make large surveys. Only one instrument, only one big project. So we have a 2.5-meter telescope that is devoted to the JPass survey. The camera that we have is 3.5 square degrees in each shot. And the main issue with JPass, that is the Havalambre physics of the accelerating universe astrophysical survey, is that we have 56 filters, narrow bands in the optical. So we cover the full optical range to have, let's say, a photospectra or a low resolution spectra at the level of 40, 90. So the goals of JPass is cosmological. So the idea is to have very precise photometric resives at the level of 0.3 errors. So we can derive 3D maps of the universe, track how the large scale structure changes with time, and provide constraints in dark energy and dark matter. So how we calibrate JPass? For that, we have the second telescope. It's an 80-centimeter telescope with a camera of 2 square degrees in its pointing, and it's doing an auxiliary survey that we call J+. So J+ is from Havalambre Photometric Local Universe Survey. He started like 7 years ago, so we already published 3 data releases, the last one in December 2022, amounting more than 3,000 square degrees. So you can access this data. We are still observing. Now we have more than 5,000 square degrees in the sky and growing. So not only the area, but also the filter system. In this case, J+ only have 12 filters. We have the usual Sloan U, G, R, I, and Z, plus 7 narrow band filters that are located in key stellar features. Why? Because the idea is that we use the J+ photometry, we made set fitting to the stars in the Milky Way, then we took the best set fitting model, we perform synthetic photometry in the JPass narrow bands, and then we calibrate. However, how do we calibrate the calibrator? So that was like a challenge, let's say, if not a nightmare. We tried several things, but just for simplicity and for the sake of this talk, at the end, we divide the problem in 2 different topics. First, the relative calibration. There are plenty of techniques in the market. We tried several. Let's assume that this is solved, even if this is very complicated. And in the DR3 of J+, what we did is synthetic photometry in the Gaia low-resolution spectrum. We found that this is enough to get a 1% homogeneous solution across all the area that we have. So for this talk, the idea is to tell you about the absolute calibration, how we know that the Gaia, let's say, reference that we use is in the AB scale, if it is. So for that, white dwarfs are in principle the best astronomical objects. If they provide you flux, in the optical is the case, so we can use it. So there are different techniques also in the literature. For example, we use the spectrophotometric standard stars. However, with the large number of filters that we have, it's unfeasible to observe them in a regular way. So in this case, as we saw yesterday, we need to really pick observation for calibration or for the survey. So we choose the survey. So we need another technique. Another way is to use white dwarfs with already effective temperatures and gravities from spectra in the literature that provide you some models that you can make synthetic photometry and compare with your data, looking for these offsets between your photometry and the IB scale. Of course, you need a spectroscopy. Now this is becoming more and more. White dwarfs with spectroscopy are available in the literature, and in the next years, Sloan 5, WIF, and Formos are going to provide tons of that. Another problem is interstellar extinction. Of course, when you have the models that without extinction, but your data that you compare have extinction, so there is an uncertainty there. And also we can discuss about why the effective temperature from photometry and from spectra really doesn't match. So at the end, you don't have a proper scale in colors. So today, the idea is to give you a different technique that we developed for J+, and is use the white dwarf locus. In other words, to use the position of the white dwarfs in our survey in color diagrams. So as an example, I'm going to present you this U minus R, G minus I color diagram. The capital G means that it's in Gaia scale. So we homogenize the photometry with Gaia first. So we select our sample using the astrometry from Gaia. We have we pick bona fide white dwarfs in the HR diagram. Also, we use the astrometry to select only those that are close at 100 parsec. So we can neglect that first order interstellar extinction. And we also put signal to noise 10 or higher in the photometry of J+. So we have the best sources in our sample, in our survey. So in the 3,000 square degrees, we end with 109 white dwarfs for calibration. And this is the location in the color diagram. So what we found is a very well-defined locus with two branches, one for DAs and the other for non-DAs. This is much clearer when we superimpose the locus expected for the theoretical models. Here you have the two branches. In orange is for these DAs, and in purple for non-DAs. And what we found very easily is that all the data are below the expectations of the models. So in this case, we assume that the models are providing the right locus. So what we need is an offset that makes the observed locus and the theoretical locus to be in agreement. As simple as that. So in that case, what we need is an offset of 0.3 magnitudes. Of course, this is for the U band, but there are other 3 bands in this color diagram. So what we do with them? In the first place, we need to assume as one reference band. So at the end, what we are doing is a color calibration. In our case, we use the R band as reference, so we don't touch the R band. And at the end, we have the other 11 color diagrams, because we always use the G minus I in the x-axis. So at the end, what we do is a joint Bayesian modeling of the 11 color diagrams using R as an absolute reference. We have different parameters in the model. We have, for example, the average gravity of the white dwarf population. This is a free parameter that we fit. We also have some intrinsic dispersion in the locus that in this case, for example, is 3%. So that means that the locus is wider than that the errors in the photometry are telling you. And also, we feed the G and the I offsets. So at the end, it's not only that we displace the y-axis, but also we displace the x-axis. Indeed, the technique tells us that the G minus I has to be adapted also by 0.3 magnitudes, so we match everything. The good thing here is that we have DAs and non-DAs, so we have 2 branches. So at the end, we have basically a unique solution for both axes. So this is very good for a stellar locus technique. As I told you, that was for the U band, but we have the other 11. I just show you here other 3 bands in which these 2 populations are split. We have the 378, the 395, and also the 660 that is sensitive to H alpha, and we obtain again these offsets. So the summary plot of the work is this one, in which you can see the offset that we need to go from the Gaia, let's say, photometric system to the AB photometric system. The gray areas depict 1, 2, and 3% differences, and we want to be as close as possible to 0. But in this case, we found clear differences, clear color turn as we go from the 4,000 Armstrong to the Z band. So in the case of the R band, we compare with pan-stars, and at the end, we obtain that we need to move just 4 millimagnitudes. So at the end, the R band in Gaia and pan-stars are very compatible. So in principle, with this, we can put our photometry that is homogeneous with Gaia in the IB scale. How do we assure that's the case? So we compare with GD153. It's one of the standards in CalSpec. You can see here in the plots, the black line is the reference spectra, both in Casper, also in the Gaia stellar spectrophotometric sample. The color dots are all photometry. There is no scale here. It's directly what we obtain in our data. We put it on top of the expected from CalSpec, and we perform syntactic photometry that are the small white dots. In the lower panels, you can see the differences that we obtain between the expectations from the spectrophotometric data and our data. Again, the gray areas are the 1, 2, and 3%. So here we see difference, but this is in the Gaia scale. So when we apply this white dwarf locus, what we obtain is a much, much better agreement. Let's say that this GD153 was not in our list of 109 white dwarfs, so it was not used in the calibration, and that these are not dedicated observations. That was observed just by chance, because we were, doesn't point to there, in the regular operation of J+. So it was like normal tiling, normal sky conditions, anything special here. So we arrived to the conclusion that we were able to achieve a 1% level precision with the white dwarf locus, using basically just our data and the models for the white dwarfs. What happened with JPass? Remember, we do all this to calibrate the 56 filters. So we started operations 1 year ago. We already covered 60 square degrees with all the filters, and 10 square degrees will be public next month with some preliminary results. At the end, we are not going to use J+ for calibration. Why? Because we learn a lot of techniques, we learn a lot of things, so we can do it much better without using J+. So basically, what we do for the relative calibration, we start with this Gaia synthetic photometry, and then we take advantage of the survey strategy, because JPass has 4 exposures, and we have half CCD dithering between them. So at the end, we just use the overlapping areas that are very huge to make the photometry homogeneous. At the end, when we compare, we are at the level of 2-3 millimagnitudes in the repeatability of the photometry. And the white dwarf locus is ongoing. We have a small area yet, but as we gather more and more data, at the end, we are going to be able to apply this technique and provide the AB scale for the JPass. So these are basically the conclusions. With this white dwarf locus technique, we were able to, we claim to an absolute flux precision in the colors at the 1% level in 12 optical bands. We will apply this to JPass in the future. And of course, our technique have good things and bad things. The good things, you use the best white dwarfs, dust-free data in your area, so the best data that you can use for the calibration. In principle, you don't need external data. You just compare your data with the models. So that's also good. Less steps means less possibility of systematic errors. And at the end, we have a consistent solution for all the filters at the same time. So for the U band to the Z band, we obtain a consistent solution. The cons, we need a very huge area, thousands of square degrees to gather a large sample of white dwarfs, because they are sparse, and those with the properties that you want are even sparser. We are, of course, limited by the theoretical models and the assumed filters transmission, but as most of other techniques are. And we provide some color calibration. At the end, one reference band is needed, so perhaps a global scale can be adapted. That's all. Thanks for your attention.
Okay, are there questions? Oops, I should turn this on. Are there questions? I'll shout it.
So you had the correction you need to do. It had a very particular shape.
Yeah.
Do you have an idea why that shape?
Yeah, at the end, when we did the homogenization with Gaia, we found magnitude terms, color terms, extinction terms. So Gaia is not very well calibrated, but it's homogeneous in all the sky, let's say. So at the end, what we are seeing probably is the problems in the calibration of the average star that we are using to make the homogenization. So at the end, it's like if you look at that, it's like F star or something like that. So probably this is the average star that we are using for make the homogenization. And this is the difference between that particular star and in Gaia. So perhaps if you go to other colors, you have other problems or other offsets, as we saw. But probably this is the offset to the AB in the average star that we use. This is our guess.
So if you pick different kinds of stars, there's OB stars or A stars, you might get.
Yeah. We found at the end in the homogenization, we use all the stars, right, from very blue to very red, and you see color terms and a lot of things. So, yeah.
Okay, are there more questions? Looks very quiet out there. Okay, well,
I'll take one.
Something there?
What do we do next?
Something there?
Sorry.
A question.
What magnitude range does your survey cover?
Well, it's the limiting magnitude is more or less 22.5 is the limiting magnitude. So at the end for calibration, we are at the level of between, let's say, 16 and 18, 19. So this is the range in which the signal to noise is large enough.
Okay, and where do you saturate?
It saturates at 12, 13, more or less.
Okay, more questions? Okay, who is our next speaker?
Recording doesn't work online, so I want to take it.
So we.
Yeah. So let's try. If it doesn't work, it's gonna go live.
If you can go live, then we'll do that because we need to be.
For filters. It's amazing.
So
if he can be live, we need to go that route. Unless it's absolutely not possible, I can bring my computer down.
Next speaker to be announced soon.
Right? Yeah, if he has it, that would work better.
You just show it.
Should still be connected. Yep.
Are you online, Luca?
Yes, I do.
Okay, great. Are you able to share the slides?
Yes. Let me just try and I'll get it started then.
Thank you. Sorry for the manage.
No worries. Yeah.
Sorry.
No, all good.
Yeah, just let me know if you can hear.
We can hear you.
Okay, very good.
Yes, sir.
Let me see.
Go ahead and share again for me.
Kevin, can you see?
That's our screen right now. Wait a second.
You still sharing?
Luca, you can share it for us real quick. If you are, can you stop the share and share again?
Okay.
Thank you.
I want to zoom in on it.
Yes.
Can you?
Almost, yeah.
I'll just get started. Hello, good day everyone, and thanks for inviting to give this talk. Unfortunately, I cannot be there. I'm trying to follow online and catch up with the talk. But please don't be. Can you hear me?
Yes.
Yeah, we can hear the recording.
Yep, all good. Reach out to me or my email is on the slide. I'm very keen to engage despite of not being there. My goal for the next 20 minutes or so is to guide you through a journey on how we can use stellar properties to reach a % accuracy in the absolute calibration. And the reason this is relevant is because it provides an independent way of doing that, as well as can be used to transfer the calibration from the infrared to the ultraviolet. In fact, I should say from the near infrared to the near ultraviolet, because this is the range that I'm going to discuss. And the relevance of the absolute calibration is broad and diverse, much like the people attending this conference, addressing different astrophysical problems. The joy and the sorrow of working with the absolute calibration cover several decades in terms of the magnitudes, the year we have been tackling this, the wavelength range. So here I'm showing a few examples over the past few years from trying to determine the fate of the universe, the Hubble diagram. Whether you combine data from different surveys or not, you're still covering a range of redshifts, which means a range of different wavelengths and filters. To testing of the cosmological principle, here I'm showing cut-wise quasar density plot to study the amplitude of cosmic dipoles. Down to the size of the Milky Way, I'm showing a color-coded map by the metallicity of stars in the Milky Way, where the metallicities are coming from photometry. And obviously, the calibration of the photometry becomes very relevant. Down to the size of a star, here I'm showing visibility plots. And once you know the size of your stars, you can derive the temperature and eventually the flux, which is the direction I'll take into this talk. But all of this really is just to say that a proper absolute calibration of the data underpins vastly different science questions, and in fact, any science question I can think of. So this is the landscape that we navigate, okay? We can usually rely on the absolute calibration with the limits and caveats that we know, and then we address our science. Or we can take a different direction in the case that we trust something else and we ask ourselves, how can I improve the absolute calibration? And in this case, I argue that we can trust stellar effective temperature, and I'll discuss how we can use these stellar effective temperatures to improve the absolute calibration. And the fundamental reason this works is because the effective temperature is a measure of flux through the Stefan-Boltzmann relation, where here there is this dilution factor which comes from the angular size of the star, of a star, theta. Okay. And although I'm using temperatures here, another possibility, for example, would be using the stellar locus, and I believe other talks will talk about this, so I'm not going to focus on this particular topic. But before I get into the details of how we convert or we pass from temperature to fluxes and absolute calibration, I want to introduce some formulas to highlight the relation that there is between temperatures and fluxes. And so this is provided by the infrared flux method, and this is the relation that you have to deal with when working with the infrared flux method. On the left-hand side, you have the bolometric flux and the infrared flux measured on the top of the Earth's atmosphere. And on the right-hand side, you have the same quantities, but defined on a surface element of the star. So the model flux and sigma t to the fourth. Now, the left-hand side comes from the observations. The right-hand side comes from the model, but typically the model dependence, if you work with FGK type stars, is not very strong in terms of the metallicity and the surface gravity because you're working on the Planck tail. And if you have the model to start with, you have your observations, then you can derive the effective temperature. And typically the way this is done iteratively by converging on TF. And if you have, let's say, 3 infrared bands, JH and K, then you take 3 different temperatures and you average those to take the mean. Of course, if you have reddening, that will enter the observed magnitude, and it can have clearly a large impact, and I'll discuss that later on. And this plot is just to put in a figure what I said. You have multiband photometry, and your goal is to recover the bolometric and the infrared flux from this photometry, and the more bands you have, the better it is. And clearly, like, the critical and crucial aspect of doing this is that how you convert magnitude into fluxes, and I don't really have to make this point to the audience because we are all aware of the importance of this. And just to give like a figure of merit for like, say, 1% change in absolute calibration, that impacts the effective temperature at the level of 20 Kelvin. And over the years, different temperature scales have been proposed, sometimes with differences of the order of 100 Kelvin. And the reason for those are ultimately related to the absolute calibration that was used, very often based on Vega. We know that Vega is not ideal. In fact, for the sake of what we're doing is more of a concept, right? What you want to know is, based on the definition of the Vega system, what is the flux that corresponds to a certain magnitude? And the same question applies if you were to use the AB system, for example. What's the flux based on that definition of the AB system? As a matter of fact, when using Vega, we use different templates for different wavelengths, and then we adjust those, and I'll discuss that later on as well. And again, to put my words into an image, this is what happens when you convert fluxes into magnitude. If you don't do that properly, you have different offsets and different filters, and what you want to do is to try to iron out those offsets so that then you question to address is how do I iron this out from the ultraviolet to the infrared? And the last point I want to make is that the modern implementation of the IRFM are based usually on the two-mass system. And this is also the system that I'm using in the infrared, whereas in the optical, I'll use everything from Tycho 2 to Gaia and everything in between. And the question is, how do you obtain an absolute temperature scale? Well, in principle, you obtain that from fundamental measurements such as interferometry. In practice, you face the usual problem. Stars with reliable angular diameters are saturated in modern surveys, and very much so in the two-mass system. So you can go fainter with interferometry, but then the reliability of your angular diameter decreases. You also get reddening to complicate things further, so you want to avoid that. And what I'm arguing here is that the solution to this problem is provided by solar twins. Now, this is an old idea, dates back to several decades ago. And at the time, more than twins, we were talking about solar-like stars or solar analogs. But now we really have a high purity sample of twins which have been identified spectroscopically. And this is very much thanks to the work that was initiated by Ramirez and Menendez. So the way they identify their twin is based on a purely spectroscopic differential analysis using the relative difference in equivalent width and equivalent width versus excitation potential to gauge a relative difference in chemistry and temperature purely from the spectrum. Okay. And here I'm showing the comparison between the solar reference spectrum and the solar twin. And you see that virtually the red and the black line are on top of each other, meaning that indeed you do identify a very high confidence twin. The other point is that most of these twins, or actually all of these twins, are very nearby, meaning that there is no reddening to complicate things any further. So the temperature for solar twins are derived using Tycho 2 and 2 mass photometry in the IRFM, and the absolute calibration in this band is then tweaked to improve the consistency among different bands. It's done on the twins, but here I'm showing it on a broader sample of 400 stars, which define the absolute temperature scale. You see in the J, H, and K band, the consistency of the temperatures that you obtain from these bands before up the top and after down by the bottom. You tweak the absolute calibration. And this tweaking is usually at the level of 1% or 50% maximum. And the two mass zero magnet fluxes that you determine with the solar twins are in excellent agreement with the state-of-the-art near-infrared determination that recently was performed by Rike. So the agreement here is in K band is at the point of 0.1%. So at the time, we estimated that we had a typical uncertainty of order 100 of 20 Kelvin or 1% in fluxes on the accuracy. But this agreement really makes me hope that we can do even better than that. And this scale is what I'm going to refer in the rest of the talk as the 2010 or the absolute temperature scale. So this temperature scale is then transferred to brighter stars through JHK photometry from the SAO system. This is done using stars in common with the two mass scale I introduced earlier. Now, the interesting part is that the SAO system is based on Sirius rather than Vega. So the absolute calibration in this case was obtained using a Kurtz template for Sirius, and then changing the flux scale to go on to the absolute two mass temperature scale. And when you do that, again, there is very good agreement with the determination of Rike. And I recall that the 20 Kelvin or 1% in flux was the target accuracy. Here you see that, in fact, you're slightly better than 1% in the J, H, and K of the SAO system. And all of these indicates that even when you go from two mass to SAO, from somewhat fainter to brighter stars, you're really well within this target accuracy. And since now we have bright stars, we can also test against interferometry. In fact, you can use the IRFM to gauge into systematic errors in interferometric measurements when stars are poorly resolved. So here what I'm showing is the comparison between the IRFM and interferometric temperature as function of the angular size. Now, there is no reason to believe that the IRFM has a dependency on the angular size, yet you see this trend very clear, pointing out that there might be some issues in some interferometric measurements shown with the black circles. The red circles then are other interferometric datasets where there is a very careful sampling of the visibility curves, and there you have near perfect agreement. What about transferring to fainter stars? Two mass is still using the infrared, but in the optical, then Gaia BP and RP from DR3 are used, and again, to calibrate against the absolute temperature scale I introduced before. I note that the G magnitude have not been used because in this case would be redundant to the BP and RP, since the goal here was to determine temperature scale, not to test the flux scale. But in calibrating the absolute temperature scale, there is a small offset of 70 Kelvin in the sense that the Gaia BP and RP are on average 1% too faint. As I said before, the purpose here was to get reliable temperatures, not to test the Gaia flux scale. So only a shift in temperatures is applied. There is no adjustment on the Gaia flux scale. But for the purpose of preparing this talk, I had a little bit more of a careful look into that, and I'll discuss that in the next few slides. So this plot is just to show that you can indeed derive very tight color temperatures and color flux relations using different combinations of Gaia and mass photometry, where the giants and the dwarfs are now nicely showing off different trends as expected. So I mentioned a 1% flux offset in Gaia if we were to trust the effective temperatures. So how can we derive these 0 points offsets? So here I'm just doing a sketch to show how this is done. You take stars with known effective temperature, for example, the stars that you use to define the absolute temperature scale. Then you keep the infrared absolute calibration fixed. The reason for that is because it performs very well, so we trust it and we keep it fixed. And then we introduce one band at a time, varying the 0 point of that band in the RFM. And then with that band and the infrared, we get an effective temperature, and we benchmark the final effective temperature to the input one and find the 0 points that provides the best agreement. So the method is differential in the sense that you are benchmarking stars against themselves. You're using the same the same metallicity, the same surface gravity, the same reddening. You're just changing filter. Okay, and if you deal with the AB system, this is the relation that you need to convert magnitude into fluxes for a magnitude in a given filter M. And the only unknown quantity here is the 0 point epsilon, assuming the transmission curve T is well characterized. And this quantity are just constants defining the AB system. So this idea has been applied to the SkyMapper survey. SkyMapper survey is a fantastic data set used for various science questions. DR4, data release 4, has been released a few months ago, 700 million objects across the southern sky. If you're interested to this, please go to the website and download and play with the data. This plot shows the transmission curves, long like GRI-Z filters, plus the UV down here in the blue side, to which I want to draw your attention to. These filters are similar to the Strömgren UV, and they have been very successful to identify metal poor and very metal poor stars, which is one of the cases that we are addressing here at the ANU. And for historic context, I point out that the data release 1 was calibrated on other surveys in the optical, plus extrapolation in the UV. DR4 now is entirely based on the Gaia XP spectra. And although I'm talking about SkyMapper, I also want to mention another multi-band survey, which is calibrated on the XP spectra. This is J+, they're doing a fantastic job. And in fact, I look very much forward to listen to some of those talks. So here I'm showing the relation between photometric 0 points and the average temperature difference determined using stars which define the absolute temperature scale. And these different panels are for the different filters, U, V, GRI, Z. And you see that the slope goes from being steeper in the UV, 0.1 magnitude every 100 Kelvin, to be milder at longer wavelengths. And if you draw the intercept at 0, that returns the average 0 point. Okay, so obviously this isn't an average temperature difference. There are finite trends as function of temperature. You can understand that a hot flux is more flux in U than a cooler star, for example. There is also a reddening dependency, since different filters have stronger or weaker dependence on extinction, as we know from the reddening coefficients. So reddening has a dependence, but it's a second order effect. More importantly, since these stars that define the absolute temperature scale are spread across the sky, you can check for spatial variation of the 0 points. This is what I'm doing in the next slide. So what we want to do is to determine the epsilon quantity, the 0 points that I showed a couple of slides ago. And here I'm showing the 0 point needed to bring the SkyMapper DR1 onto the AB system. And I'm plotting this as function of galactic latitude, where the left-hand panel is for the U band and the right-hand panel is for the V band. And I recall these 0 points are determined from the temperature inversion. The gray crosses are individual stars, and the red line is a fit to the mean trend. So there are very strong trends with galactic latitude, and this is due to reddening correction that were used to calibrate the data release 1. And if you're a pessimist, this plot shows that two of the hardest things to deal with, reddening and absolute calibration, they conspire together to make your life harder. But if you're an optimist, you think the temperature method didn't know anything about the SkyMapper calibration. It just cares about temperature. Yet it's able to uncover this trend, which personally I find remarkable. And by now, you probably guess I'm an optimist. So what's the practical impact of this? Well, my main science driver is doing galactic archaeology. And if you calibrate photometric metallicities, because of the spatial dependence of 0 points, which I'm showing here in the top panels, you infer a metallicity gradient as function of galactic latitude. You see that there is this law, but this law has nothing to do with the intrinsic gradient that the Milky Way may or may not have. In fact, the calibration, you want it to be exactly flat on the 0. And this is what I show now in this other slide, where if you do correct the 0 points, then indeed you have no spatial dependence as expected. So epsilon is this value that has to be subtracted to DR4 to get onto the AB scale. Now, what happens when I subtract data release 4 to data release 1? Well, DR4 is on the AB system. If that's the case, then the difference, DR1 minus DR4, should return the epsilon value, okay? And there is every reason to believe that DR4 is on the AB system since it's tied to the Gaia XP spectra. So this is the moment of truth, and let's look into that. So now the red lines in the panels above and below are the same, and the trend that was predicted in 2019, shown in red, is now recovered very well with the measurements which were done earlier this year. And I find this a very convincing evidence of the validity of the method of inverting temperatures. Now, in U band, there is near perfect agreement. In the V band, the trend is correct, but I give you that there is a bit of an offset, right? So if I plot this offset with a blue line, dotted blue line here, that amounts to about 0.06 magnitude, meaning that the SkyMapper DR4 V magnitudes are about 6% too faint. Now remember that DR4 is tied to Gaia XP. So what's going on? Let's try to close this loop. The absolute temperature calibration agrees between 1% with independent studies in the near infrared. The absolute temperature calibration agrees within 1% with Gaia BP and RP photometry. The SkyMapper DR4 0 points are calibrated onto the Gaia XP spectra, yet the absolute temperature scale disagree at 6% with SkyMapper V band. So let's take a closer look on how the 0 points are determined in SkyMapper using Gaia XP spectra. So these 0 points are determined for each field of view, roughly 5 square degrees, and for each field synthetic magnitude from Gaia XP spectra are computed using stars with good signal to noise. And then these magnitudes are used to determine the 0 point that you need to standardize the observations. Now, the SkyMapper U-band filter covers the range 300 to 390 nanometers, but Gaia XP starts at 320. Actually, the usable part starts at 340. So to compensate for this shortcoming, a correction is used to go from 340 nanometers to 300. And this correction is based on the CalSpec spectra and depends on stellar color. So effectively, the U-band is calibrated against CalSpecs. And that sort of makes sense because in the comparison with the U-band, I see very good agreement. Different story for the V-band. The V-band is entirely based on Gaia XP spectra. So is the 6% disagreement in V-band due to Gaia XP? And to be fair, there are issues and caveats in the Gaia XP spectra, and those are extensively discussed in the Gaia data release papers, as well in this other paper by Wang that was recently published. And the reason this is relevant is because CalSpec is the gold standard and underpins the Gaia spectrophotometric standard stars, which are then used to calibrate Gaia, okay? So to close the loop, you would expect that there is then agreement between Gaia and CalSpec, yet the V-band is indicative of issues in the XP spectra. So here what I want to track is these offsets with the temperature methodology I introduced and see if I can make sense of it. What I'm showing now in these plots is the ratio between CalSpec over XP spectra, taking stars with good STIS pedigree and focusing below 400 nanometers, which is the V-band filter sits. So these patterns are color-coded by BP magnitude, blue for bright, red for faint. There is a bit of a trend with magnitude, but there is no obvious rainbow. However, there is a very clear trend with color that now I'm showing with BP and RP as function of BP and RP in different bins. And again, these trends below 400 nanometers are acknowledged in the Gaia data release paper, along with other trends at longer wavelengths, which I'm not discussing. And I should also mention that these black lines are black body stars. I'm now using the the ratio between the planned fit and the XP, and only taking stars for which the uncertainty of flux in the UV is below 20% on average or so. Hence, there is only a couple of those, but I know there is more black body stars, and in fact, I very much look forward to one of the talks discussing the black body stars. What you can see from this panel is that the XP spectra are systematically fainter for blue stars and systematically brighter for red stars or cool stars, okay? How are these trends fitting in with those derived with the temperature approach I discussed? Well, I remind you that that approach tells us that V magnitudes are systematically fainter. So the V band 0 points are based on Gaia XP spectra using stars with the best signal to noise, and in the UV, these are primarily early type stars, which are indeed systematically fainter, okay? So effectively, what I did here has been to use the temperature approach to reverse engineer what's happening with the sky mapper calibration. What about the temperature agreement in BP and RP I mentioned before? At the time, I told you that, that's at the level of about 1%. And what I'm showing here is a plot with the difference in BP and RP magnitudes, which are computed using CalSpect and XP spectra. And the use of BP and RP magnitudes means that now you're integrated across a broad bandpass. So not just focusing on those differences in this tiny part of the spectrum, but across a much broader range. And you see that hot stars are increasingly fainter in BP with a magnitude-dependent offset, and then they level off at the level of 1 to 2% in this range of colors. The RP magnitudes are somewhat systematically brighter, and the temperature scale is anchored using FGK star, K-type stars that live into this color range here. So you have slightly fainter in BP, slightly brighter in RP, and that gives you the 1% 17 Kelvin that I mentioned before. So what are my conclusions then? Well, I'd say that there is excellent agreement at the 1% level for the near-infrared absolute calibration via solar twins with the latest determination. And this means that the 0 point of the temperature scale is robust, and I show how it can be transferred to bright and somewhat fainter stars. The other point is that the inversion of the temperature scale can be used to improve the absolute calibration. The method has very little sensitivity to metallicity surface gravity and somewhat on reddening. And importantly, the method indicates systematics in the XP spectra. Now, these systematics are known by other means as well, and the ones that I find are consistent with those determined by spectrophotometry, but interesting, are obtained to a different data set and a different entirely approach. So far, the method has been applied to somewhat bright stars in the range 10 to 50 magnitude or so. The natural extension will be then to transfer the two-mass absolute temperature scale to other infrared system, some of which I mentioned here, plus the optical as well. And I'll stop here and I'll take questions. Thank you. Can't hear the audience.
I'm curious if you've tried pulling in data from like lunar occultation measurements from like the 1970s through 1980s that might provide some additional fainter stars that you could use for calibration beyond interferometry.
Good point. Yes, I thought about using those measurements, but I have not. I think the typical precision of and accuracy of those measurements through occultations is not very high. And yeah, and by nowadays I think there is like a large suite of like interferometric measurements that I just decided to use, but definitely it's something that could be looked into.
Okay, are there more questions? Aha.
What are the prospects for doing better than that 20 Kelvin uncertainty in the true scale? Like, are there ways we can beat that or get that down a little bit more? Or are we really stuck with about 20 Kelvin at this point?
Well, I mean, if you're happy with 1% precision, then you're sort of stuck at the 20 Kelvin, right? And I think, the whole point of this meeting is, can we break the 1% and go beyond that? And, if that's the case, yes, then we can improve the temperatures in that sense. And let me just make the point here that, the 20 Kelvin is on the 0 point of the temperature scale. Of course, individual stars, they have typically, an error which is larger than that, because then you have like different issues. But so from the point of view of, getting the temperatures to better than 20, yeah, if the absolute calibration gets to below 1%, you can on the 0 point. For individual stars, to be honest, the typical error budget is then like, in a good case, is maybe 50 Kelvin or so. And so, like, does it even make sense to define a temperature to better than that? That's the other question, right?
Okay, time for another question.
So if you had to make an observation program with the VLTI or with CHAR, how many stars, and what would be the characteristics of the star that you would like to do and to try to get the angular diameter?
Yeah, okay. So definitely you would like to have nearby stars because you want to try to avoid as much as possible reddening. And you'd like to span a reasonably large range of temperatures, right? So that then you can calibrate across not just, say, like a narrow range of GK type stars, but really across the broader spectral types. So those would be the two requirements. And are those requirements orthogonal to some extent? Because if you take very hot stars and you take, red giants, and you want to span across the HR diagram, ideally, then you're bound to take like some of the stars are far away and then you have reddening. So at the end of the day, it's sort of like trying to compromise to what you can accept and what not.
Oh, there's a question over here.
I have a comment because I'm talking to the next speaker. He points out a recent paper by Andrea Riccici on lunar occultations. So just enter that into the record.
Okay, you've got an assignment. Okay, any more comments or questions? Well, then I guess we need to start the adventure of finding the next speaker. Let's give Luca a round of applause.
Thank you. Thanks a lot. It would have been great to be there.
Luca, this is George Ricci. I hope someday we actually manage to connect.
Valentine, can you hear us?
Yeah. Yeah, I can. Let's see how this works.
It's all yours. Just share screen when you're ready.
Okay. Do you see something?
Yeah, we do.
Okay, let me go to a slideshow. Okay, first, thank you very much for giving me the chance to do the presentation, this presentation, and to advertise our library. And I'm really sorry I couldn't come there. And I have to say that I regret I regret very much not being there because of amazing talks that I heard. And I also have to say that I have not made a secret agreement with the previous presenter because despite the similarities in our conclusions that you will see shortly. So the abstract that I have, I think I'll stop the video to save some bandwidth. Okay, so the abstract is very long and so on and so forth. So, oops, this? I press the wrong button, sorry. The abstract is very long, but I will try to summarize all this in a few words. And basically, the goal of this project is to generate a spectral library with very reliable spectral shapes. And the second step is to calibrate them using, calibrate them using space-based data. And when you probably start to realize that I'm going to arrive to Gaia as well at the end. So reliable space shapes, how do spectral shapes, how do we do that? We do that with the Muse, which is IFU at the VLT. Just few words about what this instrument is. It's an optical 1x1 arc-minute IFU that covers wavelength range from essentially B to I, 465 to 9300 nanometers roughly, and it delivers spectrum with resolution between 2 and 4000. Among these many numbers, you probably also need to know that the spark cell size is 0.2 arc seconds. So the sampling is excellent, but in our case, we observed extremely bright stars, and in some cases we had to defocus. So it was not the spatial sampling, but the field of view that really helped us, because essentially we have no slit losses. The instrument, just a side note, has also a narrow field high resolution mode. It can work behind the AO, but that's beside the point of my talk here. So a bit of propaganda, okay? The data were reduced with our excellent ISO pipeline, and you are invited to look at the papers down there, and you can ask some of ISO people who are there on the spot for more details. So what did we do? We took spectra of 30-some extremely high, extremely bright stars that have been very well studied, have reliable spectral types, effective temperatures, surface gravities. And we tried to, we obtained a spectrum with signal to noise in order of hundreds. We are not the first ones to do that. There is the Miles library, which you see here, that has about 1,000 stars, but the signal noise is not that high. There is the X-Shooter spectral library that has 800 stars with reasonably high signal to noise, but the disadvantage of this library with respect to ours is that the spectrograph that was used to take the spectra is shell, and there is a little bit of disagreement between the different orders, so that continuum shape is not very reliable. If I have time, I'll come back to this later on. This on the left you see surface gravity versus effective temperature diagram showing where our stars are. On the bottom there is a histogram of the spectral types. We try to populate reasonably well all the spectral types. Our strategy was to obtain 6 spectra on 6 positions on in the field of view, exactly on the same 6 positions on which we observe spectrophotometric standards. So high order systematic effects cancel to some low order systematic effects, sorry, cancel each other. And then we combine that and we measure the signal to noise from the combination. This sequence of 6 spectra is repeated as many times as necessary to build a signal to noise in the hundreds. And this is one example. The red spectrum, the red line here is the X-Shooter spectrum with higher resolution, but you see that the continuum is slightly, the shape of the spectrum is slightly different. This doesn't mean that the overall shape of the X-Shooter spectrum is wrong. It's just that this star is highly variable, and this is an issue when you start observing obtaining data with this kind of quality. And you can see the scales, 10 to minus 13, 10 to minus 15. So we're talking about many hundreds of signal to noise. We have also some serendipitous stars that failed in the IFU, and we also have data for another 29, I believe, stars that I'm working on now. So what happens? These are two more stars to show you how good the spectra are. Here is this comparison, that a little bit of elaboration of the comparison with XSL library. You can see that colder stars tend to be variable, show worse agreement, while hotter stars that generally are more stable have better agreement, but it's not always the case. In a way, this comparison is with other comparisons that will come up with Gaia later on. This is not really, I'm not really trying to make a statement, oh, these guys are wrong and they know what they're doing. I mean, this is just a different type of data set. And in fact, I think we just complement each other very well. So, now comes Gaia. So this was our secret door to the absolute calibration. That was the idea, at least. Here are two spectra taken with our library and with the high-resolution spectrograph of Gaia. So unfortunately here, I mean, first of all, I have to say that our data were taken at conditions that are not photometric. So, we stressed on what we do best. We do shape of the continuum because we have no slit losses. But the absolute calibration we cannot do well because it's extremely expensive to do multiple observations in photometric weather. So we were relying on Gaia. However, you can see already that there are some issues. And in both cases, so on the top are the spectra, middle panels are the residuals. The spectra are normalized to 1 here for display purposes. So the deviations here are, the range here is plus minus 1% on the left and plus minus 2% more or less on the right. And you see that there are systematic slopes, and this is alarming, okay? And indeed, the histograms of deviations are far from a nice Gaussian resolution distribution. So obviously we are dominated by systematic errors. Now, this is the more worrisome plot, and this is the comparison with the lower resolution spectra that have wider spectral coverage. And so the mu spectra are in green and the Gaia spectra are in red. And I have smoothed our spectra to match the resolution, the average resolution of the Gaia spectra. And okay, so with this all-star, things look reasonably good. Okay, the distribution is actually very nice here and looks to some extent Gaussian. But as we go further, you see, there is this bunch, this part of the spectra below 64,000 angstroms that shows systematic deviation. And unfortunately, as we go further and make more comparisons, you'll see that this seems to be a pattern. And indeed, there is this double peaking histograms. So let's look at the stars are sorted by in spectral types. So O, B, etc., A, etc., etc. Sorry, did somebody say something?
No, but I should say that 5 minutes.
I mean, it's not, yeah.
Yeah, thanks. I'm getting there.
5 minutes.
Thanks. And as we go further, you will see that there are similar problems in essentially every star. I mean, the distributions of the residuals are very symmetric and bimodal. And indeed, we have this systematic difference on the blue. And of course, in some cases, there are really bad failures. And so this is this kind of thing I don't use in the analysis. And in the red, my normalization doesn't work very well because there's virtually no flux in the blue part, so I cannot tell anything. But essentially now I'm kind of stuck, and I'm very worried how to process, because I have a problem with the agreement between our presumably very reliable slit losses free shapes and those of the Gaia spectra, which were supposed to be on which we're supposed to use our spectroscopic our flux calibration. Just a side note, to see what is happening, I compared our spectra with the shapes of the X-shooter spectra, and the agreements are not very good. As you see, there are systematic agreements, and they are different, essentially. In some cases, it's convex. In some cases, it's the opposite. So the continuum doesn't seem to be terribly reliable here. Just a side note, another side note, we calculate, this could be of interest to people who do indexes. Our indices agree very well with the Lick indices. And now, to summarize, so first, we take the advantage of the IFU, and I saw that in other talks that other people follow the same idea, take the advantage to reduce the slit losses. Our spectral range is quite reasonable, and the resolution is good for many applications, except we suffer from one problem, that we don't have the bluest part of the spectrum that can be taken in the ground. But I think in the future I'll fill this up with blue muse when this comes. The signal to noise in our data is great. And finally, and what's most worrisome, is this systematic difference that our presumably very reliable shaped spectra and the spectra of Gaia. Here on the bottom, you have a QR code that shows where you can get our spectra. You can get them from Vizier as well, or from the ISO Muse webpage. And you can also get this stuff from the ISO Science Archive. Now, leave this page, and I'll take questions. Thanks very much.
Okay, are there questions for Valentin?
Hi, Valentin. Thank you for a great talk. I had a question about beyond your issues with the continuum when you compare to Gaia and other observations. I saw a couple of stars where the absorption features are not there in the Muse data. Maybe in slide maybe 15 or 14.
Okay, let me share again and see. So keep in mind that which slide?
I remember the star HD 160345.
You read.
Do you remember the spectral
the
type?
top left, the star. That one. This one.
I think this is a failure of the Gaia spectrum, because it's obviously it's not right.
Oh, okay.
So I think this is not. I mean, you see that they go to negative values, so I think it's not.
So it's an artificial feature in the Gaia spectrum. Okay.
Yeah. So this means that they cannot be taken at face value.
Okay. Yeah. No. That makes a lot more sense. Thank you.
Yeah. Yes.
Okay, more questions or comments? Okay, is Everett up next?
He is. Everett, are you about what?
Oh, maybe that's.
Did I stop sharing because I didn't press anything?
Yes, please stop sharing. That will be good. Ariane Lancon said, as one of the SL makers, I can confirm we should be careful using the SED of individual objects. The averages should be trustworthy individuals.
Okay, and now from the office right next to mine, Everett Schlauman.
Can you,
Okay,
can you hear me
Everett, take
okay
it away.
and see my slides?
Yes and yes.
Thank you. Okay. Hi, I'm Everett Schlauman. I'm an assistant research professor at the University of Arizona. Appreciate you letting me participate remotely with small kids at home, and this way I'm marginally decreasing my carbon footprint. So I'm going to present work that's done with contributions from George Ricci and the Absolute Flux working calibration coordination team. I'm going to try to present this as in a fairy tale form to try to keep you awake. So it's also called JOST and the flux stock. Once upon a time, there was a calibration flux stock with the ground being the brightest stars of the sky, ties to angular diameters, NIST, and the sun, and then transfer stars, some examples shown here, to fainter magnitudes. This is growing all the time, and the hard work of folks in this room and out of this room. And it's looking really excellent. These are like the gold coins that are being brought back from this beanstalk. So when we were building the program for JDOS-T calibration, the original program is nicely summarized here from the plots that Carl Gordon made. It's got updates to these in his paper showing the highly vetted stars in the program as a function of wavelength. And then on top of that are the brightest levels, so the subarray saturation limits at the high end, and then the 200 sigma 1 hour sensitivity limits on the faint end. And the black circles here show the full frame saturation limits. So we have, for these three types, the hot stars, the G stars, the A stars, we have these great calibrators, but most of them are too bright for full frame imaging. And so the giant skeptic might say, fee, fi, fo, fum, I smell problems with your aperture sum. Many programs in full frame, your cal stars are not observed the same. So the goal here is to add fainter targets, and we've seen a lot of the good work on faint white dwarf stars. And then the goal here is to also add fainter G stars for use in calibration. And the technique was to try to find open clusters where we can identify near solar analogs as close as possible. And also an advantage with the clusters is you have many targets within, potentially within one pointing. So we selected clusters based on their properties. Ideally, their age would be several gigayears. So the G-type stars could be in the main sequence, and so don't want to be too close to the main sequence turnoff. Extinction should be as small as possible. So we were able to get below EB minus V of 0.1. We want their distance to be significant enough, like distance modulus of 12 or greater, so that they don't saturate full frame modes. Metallicity as close as solar to possible. NGC 2506 is a little lower metallicity than idea with FE over 8 of minus 0.3. Angular size should be compact enough to fit within a reasonable JDOS-T footprint and to have ancillary data for identifying standards and calibrating them. So here, returning back to the original program of single stars, we identified 3 clusters and we couldn't find something that satisfied all the ideal properties. So there are compromises on each cluster for various properties. I'm going to focus more on NGC 2506, which was observed with JWST because it is below this full frame saturation level. So here are the color magnitude diagrams for these 3 clusters. And NGC 2506, which we focus on, is shown in the upper right. We identify the main sequence stars and then down selected the ones that were closest to solar color for spectroscopy and positioning slit masks and fibers on ground-based spectroscopy of these targets. And then we used our ground-based spectroscopy. Couldn't be, given the faintness, can't be super high resolution. So we use spectral typing to identify as close to G2V stars as possible. So here it shows some of the templates and the temperature sensitive lines we use to identify cluster stars that are closest to G2V spectral type. And when we down select those, we're able to fit about 8 of them into a NearCam 2x2 mosaic footprint for use in calibration. So this shows the footprint, and then we model these stars. You can see George's paper for this using the spectral type and the Boss-Z models. And George derived this correction to the Boss-Z models that it comes from the absolutely calibrated solar spectrum. And then also apply an extinction from the KS minus V, and then use our input ground-based photometry and JHK bands, Gaia, and pan-stars to normalize this spectrum. So here is what the cluster looks like. I tried to make a pretty color RGB image. It doesn't look all that great because it's so well resolved by JNewsT. It's actually good that it's not a super pretty cluster because it's, the stars are fairly well isolated and from each other. So this was observed in 2 programs, program 1538 with a bunch of filters, and then 1493 with 2 filters and a wider field of view. So then we do aperture photometry on the cal.fits files and basic corrections for the solid angle and circled energy with the web PSF, repeating on all files, and then median for the available files. We also do a check that this code and the methodology can give consistent results with the previous calibration. So this is the the white dwarf GD71. Using the same CalSpec model, seeing if we can get consistent results. There's still some things to track down with the double wide filters, but we're seeing pretty close agreement on the rest of the filters. So returning back to the cluster, here's a G2V star that has some of the lowest residuals. So the left shows the measured photometry using the fall 2023 NearCam calibration. And then green is the model using this corrected Boss-Z model. On the right are the residuals in percentage of the data minus the model. So then here's one of the worst stars in this sample, showing some larger deviations. This is still actively being worked on, trying to track down these discrepancies. And if we put them all together on one plot, here are the 8 near G2V stars in the cluster. There's a lot more scatter than we'd like. So I'm trying to track everything down from the ground-based photometry models to the extractions on the full frame images. In some filters, the medians are very close, within 1%. There's about half of them, it's larger than, but I wouldn't look, I wouldn't worry too much given the scatter that we're getting right now. One aside is to be aware of the mosaic catalogs. If you just straight up use the files from MAST, you can see on the right the residuals against our calibration are 50%. So really dramatic, and it's not obvious just looking at the image what's going on. It turns out that the image registration, if there are any small deviations, the outlier detection step can identify some of the cores of the stars, especially when they're undersampled, as outliers, because there's like just a small discrepancy between these images, and it's kind of hard. So Anton Kokemeyer showed how you can dig into the weight files and check for this. So something to be aware of, that getting the registration right is important for the flux calibration. So that's why we do our photometry on the individual detector images. So to conclude, we have an excellent beanstalk of calibrators. We're trying to add some targets of different types on the fader end. We've identified near G2V stars in clusters, including NGC 2506, observable with JDUC full frame imaging with NearCam and NEAREST. Preliminary analysis shows fairly large scatters, nothing bigger than 5%, but it's still a work in progress. We haven't yet leveraged the power of the cluster and the other stars in the cluster to improve the calibration. And so I think there's hope that this may turn something closer to the goose that lays golden eggs, but it's still a work in progress. So thank you for your attention. I'll take some questions if you have them.
Hey, a couple of comments, since obviously I've been working with Everett on this. First, I wouldn't make the conclusion as negative as Everett made it sound. It's the numbers scatter basically within plus or minus 2%, and this exposes some of the problems with sweeping from bright down to faint enough that we can actually do them full frame. The other comment is to get a good fit, necessary to adopt an extinction law for Article 3.5, which it turns out in the direction of this cluster that's actually found in general in that direction. And it just exposes that when we go faint, staking a standard extinction law is probably not going to be good enough. It's going to be a much bigger mess than we think. Okay, with those comments, are there questions for Everett? Carl Gordon.
Hey, Everett. My question is, I'm very encouraged by this idea of having clusters so that we can get more calibrators in a smaller field of view, et cetera, and different kinds of stars. Can you comment on the prospect of going even fainter and getting, so that we can not just get the G stars in full frame, but also A stars and other? Heard in this conference how it's important to have a variety of spectral shapes. Thanks.
Yeah, I think it is definitely feasible to go deeper. These images themselves aren't all that deep. So yeah, maybe we can revisit this cluster deeper. But definitely, yeah, we have a signal of noise on these to go deeper than the G stars certainly. And I think there are even some if you love white dwarfs, there's even a couple in this cluster maybe. So there's many different spectral types possible. I think there's a lot of hope in using the full cluster and not just the G stars in it.
So I should point out, finding this cluster was a fair bit of work. So I don't think it's as easy as just, there's a cluster. But what we really need is for Ralph is a cluster of hot white dwarfs, and then we'd really take off. Okay, Kevin.
Hello, Everett. How is the signal noise of your photometry compared to what is predicted just from the exposure time in ETC or something? The question is there some systematic in, the level 3 processing, or you mentioned going to the individual images and this kind of thing. So it'd be nice to know if there's a flaw in the pipeline that we have to deal with in order to make this much better.
Yeah, there are. It's mostly systematics dominated in wide filters. So yeah, it is systematics dominated. There's such a long chain. I can't put my finger. Definitely, it's the J2C pipeline that's the cause of the issue. But there, because it could come from a variety of places. But we definitely have more than enough photons for 1% photometry.
Yeah, I would point out the first star, I think it was G31, the scatter looked pretty bad with the error bars Everett had, but if he had assumed 1% error bars, which is not unreasonable for photometry at this faint level, everything would have looked wonderful. So there's a lot behind Kevin's question that we got to understand. More comments or questions for Everett? Anybody online? Any comments? Okay, let's give Everett a round of applause. And now I think we've run out of time.
Nice, George. Nice.
Sean Carey. Unfortunately, we haven't run out of time.
Never run out of time for Sean. If he couldn't speak, we couldn't help him.
See, Greg's always looking on the bright side of things. Well, hopefully this will be entertaining for everyone, including me, and I'm holding myself up from coffee, so I'll try to be brief. Last time I talked at a calibration workshop was in 2014 here, and I was talking about the final calibration of Spitzer IRAC. Today I'm going to talk about how we're going to calibrate a mission which hasn't launched yet. And one of the big things I want you to learn about is what NeoSurveyor is and how you can use it. So there's a whole, it takes a village to do calibration. A lot of these people don't do any work. The folks in the dark bold text did a lot. Okay, so NeoSurveyor is a planetary defense mission. It's not even supposed to do science. What it's supposed to do is look for things that could cause us a really bad day. So near-Earth objects greater than 140 meters or comets that could collide with us. So this is the kind of thing, if it hit Baltimore, it would also take out Washington, D.C., right? So we want to find these things. It's also the only mission I know that is actually responding to federal law. There's a George E. Brown NeoSurvey Act, which says that NASA has to go find all the potentially hazard objects greater than 140 meters, and there's a whole story behind that, by 2020. Okay, so somebody at NASA should be arrested, but not. Okay. We're on track to launch sometime in fall 27. Hopefully we stick to that. The principal investigator, who folks may know, is Amy Mainzer. She worked with a lot of us on Spitzer and did a lot of other work on NeoWise. So there's a lot of heritage in infrared science for NeoSurveyor. We're just heading up to Project CDR, right? It's in February. So everybody who's been through this meat grinder knows exactly where we're at now. Okay, and I already told you what the science requirements is find 2/3 of all the. We're not even going to satisfy the law. So maybe they'll cart Amy away in cuffs, or probably me if I don't run fast enough. The idea, though, is that in a 5-year mission, in a 10 to 12-year mission, which is potential because we only have nitrogen gas as a consumable, hydrogen gas as a consumable, goal is to find 90%, and that would satisfy. And also the idea is to do some science, because you have to characterize these objects to know that they could be dangerous. And plus everything else in the background, right? Okay, so the mission is pretty simple. It's based on, it's got a heritage with Spitzer and WISE. It's going to be in a halo orbit, but L1. So on the opposite side. There's a really good reason for it, because we want to see things closer to the sun, okay? The instrument is passively cooled. It's a 50-centimeter telescope, so not James Webb. It's on off-axis TMA, no diffraction spikes, which makes source fitting a heck of a lot easier. It's 2 infrared channels. one centered around 4.6 microns, kind of like WISE W2, and one centered around 8 microns, which is sort of like IRAC channel 4. So, but different technologies. These are Mercad tellurides. Field of view is large. It's 1.7 degrees by 7.1. It's a 1x4 set of detectors. Sensitivities are not bad for a 50 centimeter telescope. You're getting down to like, 0.1 millijanskis in both band passes. And the only ejectable is the cover, which is good. There's no focus mechanism. There's no filter wheel. It's really simple, right? Yeah, thank you. And it's passively cooled. And one of the things it needs is has radiators. And one of the limiting factors on the cooling is actually earth shine, because they're facing away from the sun, but because it's at L1, they're seeing the earth. Okay, so the pass bands are designed, remember, this is all designed to go find these pesky asteroids that could cause a bad day. So basically it's in the thermal infrared, and it's as red as we can get and passively cool cheaply enough, so you don't want to get fancy with cryocoolers and heck no cryogen, right? Okay, we're not doing that anymore. So we can get the 10 micron cutoff detectors down to about a temperature of 40 Kelvin. 40-ish Kelvin, and we're testing that now. It looks pretty good. Okay, so the idea is so you're going to measure these in the IR. You know their orbit. You can model their temperature by doing thermophysical modeling, and then so you're going to back out what the radius is by measuring the flux, and you really have to measure the flux to some accuracy. Now, it's not 1% the requirement; it's 7%. So we should be able to hit that, and that maps into a 15% uncertainty in the radius, because that's good enough to know if it's big enough to cause trouble or it's not, right? And one of the things is that I realized is that the impact energy goes as the cube of the size, right? So you really want to get that down pretty well. Okay, so this is what it looks like in terms of finding. So these are all the potentially hazardous asteroids that potentially we could detect through simulations. And you can see the NEO-surveyor field of regard is looking more towards the sun, more towards the center than ground-based stuff, which is always looking at, opposition, and NEO-WISE, which was in Earth orbit, right? So it was only getting like a narrow cone that got spun out. So it's going to be able to detect a lot more objects quickly. And the survey is highly redundant to track moving objects. We do a lot of dithering because we're undersampled, so there's 6 dithers in every visit. And then every position in the field of survey gets observed 4 times over a period of 8 hours, so roughly every 2 hours. And then we go back and see that same spot again every about 12.5 days later. So the idea is you go look, 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 see if anything moves, and then look again, and then try to connect motions, those tracklets are going to form into a track that you can make an orbit out of. Let's see, I got to point out this. Okay, so the whole sky's not being observed, okay, because most of the things that are bad are going to be in the ecliptic plane. But the near-Earth objects, actually, you can find them all over the place. So plus or minus 40 degrees in ecliptic latitude. So it includes interesting things like the galactic center and a lot of other interesting places, but not everybody's favorite place, right? Okay. One thing we're not doing is the ecliptic poles, not yet anyways, not in the baseline mission. Okay, let's see if this plays. If it doesn't, we'll just skip. This is just like yeah. So basically, this is just showing how the survey is going to go. So you keep going back and mapping over a portion, and the dots are when you've detected a moving object, and the green is when you've been able to make it into a tracklet. And then it just keeps going. So you're mapping out one fairly large swath of the sky in about 6 days. And then you do the flip and do the other side. Okay, so this is what we think the data is going to look like. We have flight detectors almost chosen, and we have their properties, and we look in a dark current, good stuff like that. And so now we have an image simulator where we put in those actual properties. And so this is sort of the data you'll see. So the raw stuff, you got to do some things. Calibrate it, co-add it. So you take those 6 exposures and make a well-sampled image. And then you can make nice color plots, which look a lot like WISE, but are more sensitive. So this is kind of like WISE with a different cadence and more sensitive is what you should take from it, okay? At the 2 pass bands I mentioned. Okay, so every exposure, every visit all the source detections, and this is the inertial sky, this isn't just the moving objects, are going to be delivered to the Infrared Science Archive at IPAC on a 6-month cadence. And that's data that everybody can use for whatever they want to do with it. And then every 12 months, we're going to make coads of all the data covering the sky, like make a yearly coad of that, and we'll continue to do that until we run out of money or the mission ends. You realize the mission's going to end because we run out of money. Okay, yeah. Let's see. So that's the stuff you want. Go back to you want to get this data, you want to do your own science with it, right? Because it's got some unique cadence and it'll be fun to play with. And yeah, I think it'll be really interesting for most people. Okay, but if you're interested in moving objects, near Earth objects, this is kind of how the pipeline's going to work. So you take those exposures and you do some processing. We make the nice visit image, that's the level 2. And then we take the 4 repeats that you every 2 hours, and we make difference images where you take the one you take the 3 you're not interested in, make a reference image, and subtract that, and then you look for the things that are left over. And then you can link those from visit to visit to visit. So this is like 4 images over 8 hours, and you can see the objects that are moving. And those are the things that are identified and linked and sent to the Minor Planet Center. Okay. Let's talk calibration, because that's what the meeting's about. Oh, I've got plenty of time. We've got really loose requirements on the calibration. This is the kind of thing you have to show and justify. So the thing here, which I think we've been talking about a lot is in comparing the models and stuff, is the uncertainty in the standards I'm using. And I've got a 3% allocation. I think I can get better than 1.5%. I can probably, if I listen to George, do better than that, but I may or may not, right? The largest factor here is the color corrections to the near-Earth objects, because we're going to calibrate off of stars, but the near-Earth objects are really red. They're 300K-ish black bodies, right? So there's a transfer there that we have to get. We've been trying to think about calibrating basically on asteroids, but it's really hard to do. So what this means is we need to have a really good knowledge of the relative spectral response of the system, because that's our dominant source of uncertainty. Okay, here's my boilerplate about how we're doing it. The thing that's important here is that, because I have a diversity of ignorance as far as understanding things. So I marginalize over my ignorance. So what that means is I'm going to do a robust average over each calibrator we have, and ensembles of those calibrators based on the spectral type, so tying into our model uncertainties, and then average over all those to get the final calibration factor. So I'm using as diverse a thing of spectral types as I can get to try to do the absolute calibration for NeoSurveyor. And this is also what we did with WISE and Spitzer IRAC, because we want heritage to these previous infrared surveys, so we have traceability when people go say, hey, we saw this object before. Is it the same object? Does it make sense? Okay, got to point at this. All right. Now, come on, this is the least okay, so we're going to do the calibration. We have a SV phase, which is going to last 6 months. We're hopefully going to do most of the calibration in the first month so we can tune the survey properties, because there's a lot of tuning. You know, because 4 visits might not be enough. We might want to do 5 visits on each patch of the sky. So that's something we've got to figure out. We're going to do a lot of calibration just based on the survey data, because we're going to get a lot of good, we're doing the same thing over and over and over again, right? So we get the same dynamic range each and every sample. And we're going to do photometric calibrations every side swap. So every 6.5 days, when we go from one side of the sky to the other, we're going to go over one of the poles, and hey, we're going to stop and we're going to take calibration data, okay? And we're going to do this, we're going to take as much data as soon as we can so we can understand the system, calibrate it, and then just get going onto the survey. All right, so this is what kind of a sample photometric calibration towards the either pole. I prefer the NEP because I think we have more secure calibrators there, but the WISE folks say we can do it with both. And basically, we're going to have a network of stars. We can fit a bunch of them on the field of view. We're going to move them around on each array. We're going to sample each array as densely as we can. And we're also going to get some diversity just by the fact that next time that we go and survey that field again, we've got a roll angle, right? We're going to see that's going to roll over the course of a year 360 degrees. We're going to build up a really good network. And our calibrators are going to be mainly A stars, K giants, yeah, boo, right? And solar analogs, but no solar analogs are in these fields of use. So we're going to have to pick those up specially. But we're going to do that because we want this huge baseline. I'd love to use white dwarfs. I don't think we're sensitive enough because we only get down to like a Vega magnitude of about 15 or 16.
That's good enough.
Okay, yeah, it's going to be hard though. It's going to be hard. Yeah, we should talk. Okay. What else did I have on this? Come on. Okay. So here, what the preliminary relative spectral response look like. So this is based on witness samples from the vendors for the beam splitter and the filters. It's based on preliminary quantum efficiency measurements from Teledyne. I had to do some massaging. They did not have the cleanest apparatus, so there were actually water features in the spectrum, which was a little annoying. And you can basically see that NC1 rises with increasing wavelength, NC2 falls. Those ripples are real. Those are the interference patterns from the coatings on the filters. And one of the things might be hard to see, and that's a good thing, is that there's a plot of different colors, which are the RSRs of different primary arrays as they go through the system. We have a 14-degree cone, essentially, of angles of incidence through the system as imaged on the sky. And what that does is that causes you a little bit of shift in the relative spectral responses, but it's pretty small. We're going to spend a lot of time next year testing the RSRs at Space Dynamics Laboratory, who are putting together the instrument. They have some really good chambers for that. We're going to use a Fourier transform spectroscopy, which is a kind of known method to measure the RSRs. But that method is not very sensitive to large-scale fluctuations. So one of the other things we're going to do is dedicated narrowband measurements at tie points along the different parts of the filter, particularly at the edges, to make sure that we understand where the filter bandpass edges are, because that's going to be vital. Okay? So if you just take that RSRs templates, I'm almost done, you can get what preliminary color corrections are. They're on the order of 10%-ish, and they flip like the NC1 for redder, cooler sources. Thank you, George. You can tackle me in 4 minutes. No, I'm joking. So you can see they're on order about 10%, and the differences from the different angles of incidence are rather small, right? So that's a good thing. That means we're going to check it, but we're not too worried about having huge photometric variations until we have huge photometric variations. The other thing to notice is that for the very faintest, coldest objects, there's huge color corrections, right? I'm a little scared about when people are going to look at like outer main belt asteroids, because that's going to be a harder transfer, particularly at NC1. Okay, here's just a list of calibrators and what their in-band fluxes are in magnitudes, because other folks on the program like magnitudes, so I gave it to them. All right, anyway, so here's the summary. Okay, NEO-Surveyor is an important and exciting mission. It's good because it's planetary defense, so we can have our salads as opposed to the dinosaurs. It's going to have a really interesting time sampling, which I think you'll all appreciate. The data is going to be publicly available with no proprietary period. Our photometric calibration plan is mature. It has heritage from stuff we did before. We're going to try our damnedest to get the system's response right. Future work is expanding the potential calibration set to get more diversity, because that helps me decrease my ignorance, and talking with you all kind folks about doing some cross calibration. Okay, thank you very much.
Questions or comments?
He has a comment.
Oh, way over here.
Well, maybe somebody else has a comment first.
Got his own microphone.
I'm going. All right. So I don't think this is on.
So you've got two fields of regard to either side in solar elongation.
Mm-hmm.
So over the course of a year, you'll sweep out the zodiac plus. Okay, got it. So my question is Spitzer in the field of regard?
It will be, but it'll be too faint to see.
Well, that was my next question is, can you detect it?
No.
Okay. And then a more serious.
I don't think we could maybe detect it with Webb, but
All right. So the more serious note is your list of standards. I couldn't help but notice that a lot of those are K-Giant.
They are.
And a lot of those currently have, I know they have Cohen templates, but the Cohen templates are off by a few percent. I'll point this out tomorrow.
Yeah,
What are
okay.
you
So no, that's
doing for truth spectrum.
okay. So that's a good point. So we don't use the Cohen templates, and we haven't since 2012, when Charles Engelke revised all the K-Giant templates, and those are the ones we're used because from his paper, those are tied back to MSX and 2MAS and Derby, and they do a much better job of pulling in the discrepancy between the K-Giants and the A-stars. And Ralph's not here, but he had a really great paper where he looked at the CalSpec standards that we observed with IRAC, and basically the K-Giants were here, the A-stars were here, and they were discrepant by about 1.5%, which is that bound I gave. But the solar analogs were right in the middle between the two. Now, you can say maybe you want to throw out the K-Giants, still I can understand. You're going to tell us more about that, right? But even if you don't, there's pretty good agreement between the three types of calibrators now.
Okay. But wait a minute. Carl showed you a plot that showed the A-stars and the solar analogs within less than 1% of each other.
Yeah.
And so that means that it's A-stars, solar analogs, K-Giants.
No, it's a good.
So, Carl.
I don't have an answer on that. I would say that if you want to use the K-Giants, maybe we should be getting truth spectra of them with MIRI. Okay, so that's a solution to this problem.
Yep.
Okay, the second one is much more interesting. I want to know. So, can JWST and NeoSurveyor observe the same part of the sky at the same time? I'm asking that question because if so, we might be able to help answer your question about the transformation to the asteroids, because we could take spectra of the same bloody asteroid you're observing.
I think the answer is yes.
Because that solves your problem of, knowing whether or not what that spectrum of that and what the temperature should be.
Yeah, and I think you're going to get requests for that, right?
I think, so we should talk about this because this sounds like, one NASA mission should help the other NASA mission.
I agree.
I'm not sure we need to rely on the community agreeing, if that makes sense.
Yeah, I hear you.
It sounds fundamental to making sure I can have my salad.
Yep. Good point. Yeah.
Okay.
Damn ones.
Oh, boy, there are all kinds of questions. Congratulations, Sean.
Yeah, super cool. Would you mind going back to the slide where you showed difference images and explain what's all the stuff on the images?
Yeah.
Stable it is. Just
all right. Let me. Oh, it's ridiculously stable. That's here. Hold on. Why is this so?
Just use the keyboard. Yeah.
No, I could have just used the keyboard. Okay. This one here. Yeah. Yeah. So basically, the image differencing method, as long as everything stays stable and you do the same sort of thing, getting the same orientation, is going to be really good about subtracting the inertial sky.
It's like, what are these dust clouds? What are we looking at?
Oh, that's the ISM. That's at 8 microns, you're getting the ISM, right?
Okay, so
that
won't change at all.
And that's not going to change. Now, there will be variable stars, which somebody otherwise is going to be very interested in these difference image results, right? Because they're going to pop up too. But the cadence here it's sort of interesting because it's hours-ish, right? So things will come up, yeah.
What's the pink thing on that?
I'm sorry, the what?
The pink dot on the image.
The pink dot. You mean up at the top there?
No. At the bottom.
There's a pink dot.
Second difference image. Also one on the right.
Oh, that's there's a couple of pink dots there.
That's been great.
I think, those are bad pixels, I think, that are getting maxed out, yeah.
Is it some interesting thing?
Yeah, this is really interesting. Also for the extragalactic community and variable stars. What are your plans on making these difference images public, or at least alerts, like non-asteroids that pop up?
Yeah, so as far as alerts, it's not in scope for the project. That would be a huge plus up. Having the difference images made on a rapid time scale because that's what you'd be interested in. That's also a plus up. So remember, this being planetary defense right now, they're not interested in it. Once it launches, if NASA APD says, oh, hey, and if the community says, oh, hey, this would be a good thing to have, that could be something that'd be implemented. And the architecture of the pipelines does not preclude that, because a lot of heritage for doing this sort of detection stuff is based on the Zwicky transient facility, which also is really into looking for transients for other, and it was designed for transients for other things and also finds moving objects. So the answer is we could do it, but we're not, it's out of scope at this point, unfortunately.
So Greg says there's a web question.
So there's a couple of comments. Valentine chimed in. He just pointed out that if you're going to run out of money, you just need to find a killer asteroid, and that should solve the funding.
That's a good point, yeah. or not.
Someone else pointed out that actually, if we discover the killer asteroid problem, that will probably lead to a diversion of funds.
Yeah.
I have a more serious question. Your error budget was dominated by color correction of the asteroid, but suppose that we're just paying attention to stars. How accurately can you measure a star, and how well can you compare one star with another? And I think I'm mostly interested in the 7-micron band, because the other one is kind of like W2.
Yeah, so the color corrections for things with same slope SEDs are all going to be pretty much similar, George. So that goes down by quite a bit, right? I mean, you know, we should be able to do the color corrections to better than 1% between stars, right? It's the NEOs, the star to NEOs, that's the real big uncertainty. And mostly that's because the shape of the filter just change, you know, it does opposite things, right? So for the stars, you sort of don't care, because even if you got it wrong, you got it wrong the same way for both of them.
But let's look at this chart.
Yep.
Temporal stability presumably applies to your instrument.
Yep.
So that's kind of an irreducible problem.
Yeah, it's
what is the uncertainty in the absolute reference? I don't know what that is.
Oh, that's basically taking the standards, right, and doing the transfer to Sirius, essentially. I'm throwing that in as a separate thing because people disagree. Well, it's Sirius, and it's back to the NIST standards, right? And
so we don't care about Sirius in this. So we're kind of at the 2%, 2.5%, 3% level because of the temporal stability. I mean, that's useful in terms of thinking about calibrating.
And remember, the temporal stability is an allocation, right? This, because that's something about the system response we don't know yet.
Okay.
Right? This is the thing that satisfies the system engine.
That's different from what you might be able to do.
The next comment is it's time for coffee.
Thank you.
Posters, please check out the posters, and we'll be back here at half an hour. Let's just call it half an hour, which will be
55.
Yes, so 2:55, and the discussion session will happen, as you pointed out, and it'll be on road calibration.
Very serious.
So, all right.
Not even a question.